Alright, welcome. Today we will be talking about continuity and behavior. So continuity is a huge thing in calculus, and it's best done by looking at a graph in calculator. So ignore this fact that I just had right there. Okay, so continuity. So continuity is just basically you approach, is the graph continuous? Can I pick it up? All that type of stuff. Okay, so to understand continuity, we have to understand what discontinuity is. So let's say f of x is equal to 1 over x squared. Okay. Now this graph, and just remember, you can have continuity on certain intervals. Okay, but this graph, as you go this direction, you're like, oh, okay, I have my graph. I like to think of continuity as can you draw the entire graph without your pencil, without your pencil ever leaving the paper. So right here I'm drawing, la la la, nothing problem, and then all of a sudden I go up to infinity, and I don't want to go up to infinity, so I skip it, come down over here, and draw the rest of my graph. So what I had right here was an infinite discontinuity. In other words, it is discontinuous at infinity. So that's a huge kind of discontinuity. Okay, another type of discontinuity is piecewise. So we got x squared plus 1, and then bracket x is less than 0. Okay, so there's one graph of it, and then down here, let's say g of x is equal to x brace x is greater than or equal to 0. Okay, so now this type of, and I have to do the same color. Jeez, I hate when they got two different colors. Okay, so right here we have two parts. So right here, pretty continuous, not picking up my pencil as I'm drawing, la la la, and then all of a sudden I get to undefined. That's not good. Now I have to pick up my pencil, move it down, start here, and then continue drawing up. Okay, so this is called a jump discontinuity. It's like I jumped from one graph part to the other. Okay, all right, so that's a jump discontinuity. Okay, and one of the more famous ones that you'll see, oh, excuse me, is one of the rational ones. -1. Let's put that. Okay, parentheses divided by parentheses. Alright, so this one right here, pretty simple, la la la. Moving on, so on and so on. We're pretty good. Okay, now this one, let's change this to minus. There we go. Okay, now as you can see, we're drawing the graph. It looks like I'm going to have everything, but if I go around here and I pay attention to the denominator, okay, that's going to tell me the restriction. So I go check my restriction, and all of a sudden I have a hole in my graph. This is called a point discontinuity. Okay, so we've got infinite discontinuity, jump discontinuity, you're jumping from one graph to the other, and point discontinuity, which is usually with rationals or something where you have to cancel out and get a hole. Okay, so those are the types of graphs as we go. Okay, now here's the thing though, is continuity, oh, let me go back to the graph. Alright, continuity, y equals x squared. Alright, in order to be continuous, okay, you can be continuous on the entire graph, like this one is continuous. If I were to draw forever in both directions, I would have a nice smooth parabola shape. But if you were to say, okay, I want to approach -1 on my graph. So as you approach -1, you're going to find that it is nice, smooth, and continuous. Now, You also have to check from the left side as well. Is it nice, smooth, and continuous? Yes. And then all of a sudden, is it continuous at that point? Yes, it is, because there is no point discontinuity. So you can check by looking at the graph at that. Okay, so a function is continuous at x equals c. So in other words, as a function is continuous at x equals -1, if it's defined there, that's number one. If, in other words, I get an answer. The function approaches the same value on the left and the right side, so that's number two. I approach it from each side. Okay, and the y value is also the answer. So in other words, I do have a y values here. Now, something that would not appear there would be something that had like something like this. If I had graphed, let's go the point -1, 5. Okay. All right, and then let's say for some reason this was discontinuous at that point. Okay, so this one's right here. So this one, I would have a definition. This one would fulfill the first statement. Okay, it is defined at a point, so it is negative. It is 5. It does approach it from both sides, but then all of a sudden I have a hole here. Let's pretend that there was a hole here. Well, it's up here. The value's up here. So therefore, this is not a continuous type of graph. Okay. So that's what I'm getting at on there. All right, now another thing is in behavior. Now continuous just tells you, are you skipping any parts, are you doing anything horrible, are you doing anything crazy, and you're just working through it. Okay. All right, continuity and end behavior. Okay, so continuity and end behavior are pretty. End behavior. Continuity is pretty easy to figure out once you have the formal definitions down. Okay, but end behavior is really easy to figure out once you get it. Okay, so what you have to do is you have 4 situations. You could have 1, 2, 3, or 4. Okay, so you look at the lead coefficient. So lead coefficient. Oops, let's do 1f. Or 2f's, because that's what it is. Okay, so the lead coefficient is what we want. So there's 4 situations that could happen. Okay, and we also want to look at the degree. Alright, because if we look at the degree, we have 4 different situations that could happen with the degree. Well, 2 situations, but 4 total situations with the lead coefficient. Alright, so if the lead coefficient is positive and the degree is even, in other words, the highest exponent, okay, my end behaviors are going to be left, it's going to be going up into infinity. Right, it's going to be going up into infinity. I don't know what's happening in the middle, but I know the left and right side. Alright, now if the lead coefficient is positive, but the degree is odd, okay, in other words, 1, 3, 5, 7, you know those. Okay, my end behaviors are going to be going up into the right and down into the left. So down to negative infinity on the left and up to infinity on the right. Okay? Now if my lead coefficient is negative and my degree is even, okay, it's just the opposite of what I just did for the first one. So it's going to be going down to negative infinity on the right and down to negative infinity on the left. It could change a whole bunch of stuff in there. Alright, and if my lead coefficient is negative and my degree is odd, okay, it's going to be going up to positive infinity on the left and down to negative infinity on the right. Okay? Alright, so if we take a look at a graph of this as we go through, y equals negative 3x squared. Okay, so since this is negative and this degree is even, it's going to go down. Now if I change this to a 3, it's going to be going down to the right, up and to the left. So positive infinity to the left, negative infinity down to the right. Now if I change this to a positive, now it's up to the up to positive infinity on the right, down to negative infinity on the left. Alright, and if I change this to a different degree, let's say 4, up and to the right and up and to the left is what the end behavior is going to be. Okay, now what you can do is you can use this with polynomials in trying to graph them by hand. Back in the day, they used to have to pay attention to these rules. But nowadays, you can actually graph it and see, oh, there it is. But now you understand where this stuff comes from. Okay, it's because every even function is going to be going up and to the right, up and to the right, and up and to the left for positive values in the front. And it just depends. It doesn't matter what I have here at the end. I could have all kinds of stuff. As long as the lead coefficient and the lead degree, well, not the lead, the highest degree exponent are both these two rules, everything else could be funky and I would still have the same type of idea. And then what I would use is, back in the days, if I had to use a graphing calculator, or if I couldn't use a graphing calculator, I wouldn't just plot by hand and be like, that would take forever. I could, but you could actually do a shortcut for a rough idea of what this graph is going to be. So like, for example, if I did something like this, oops, that's the next lesson, sorry. Okay, if I wrote out a function like this, y equals negative 2x to the 7th minus 3x to the 3rd plus 22, okay, something like this, I would go, okay, so my graph, okay, I would look at the exponent, okay, in the degree, and I would look at the leading coefficient. Okay, so I could tell you right now, since it's odd and it's negative, it's going to be going down and to the right, up and to the left. Okay, and then what I would do is I would find the zeros, okay, and it looks like there's probably going to be 7 zeros or 5 or 3 or 1 0. Okay, it is going to go through the axis once, and depending on how many zeros I have, it's just depending right there. Okay, so in this case I'm just assuming that it has 3, so my graph, I could do a rough sketch and it would look something like this. Okay, now if it had 5 turns, here's the cool thing. If it had 5 turns, if I had 5 zeros, let's say right there, okay, I knew my graph would look like this. Or, you know, something roughly close to that. So, you know, just by taking a look at the actual information, I can do a rough sketch and see what this graph is going to be. Now, if you don't learn this skill analytically and you just rely on your graphing calculator all the time, you're going to be really left in the dark. So you have to take your time and just look at the analytical parts of it and just see what it's doing. Alright, thank you guys very much and have a great day.